say 3 by 3 filter. And then what I'll do, I'll place this, what is the, this is the area where I want to calculate the response. So what is the center of this area? 2. Because the filter size is 3 by 3, I have to consider 3 by 3 only here in the image. Consider this is left hand side is image. Okay. Now what I'll do, 1 by 9, the center 1 by 9, I'll place over the 2. Okay. So this is the second step. Then second step is multiplication of filter coefficient with the pixel coefficient. So what I'll do, 6 will be multiplied by 1 by 9, 9 will be multiplied by 1 by 9, 7 and all other. So new value that is after multiplication is 6 by 9, 9 by 9, all this what is shown here. Okay. And what is the third step? Addition of all these values. Okay. So it is 5.89 or whatever the value. So what after operation of this is averaging filter. After operation of this, what will be happening? Okay, what will be happening that the 2 value, okay, which is shown here, will be replaced by this new value, and this is done for entire image. Okay. So how we can implement this by using filtering in the Matlab? We can do it by using IMFilter command. Okay, so there is an inbuilt function. We don't have to manually write a code for or looping I equal to or n ij equal to number of rows, 0 to number of rows, and column equal to 0 to number of columns. No, already there is an inbuilt function that is IMFilter. Okay. So what is the procedure to implement this? We have to read image. Okay, so it is color image is there. Okay, so it is papers, not papers. Okay, so what I'll do, I'll show the first color image. Okay, now we can read this. This is color image. I'll show this. Okay, you can see RGB image. Okay, fine. So how to perform the filtering operation using Matlab? You have to read the image. Okay, then you have to apply, you have to create a filter. In this case, a motion filter is created by using F special command, and then filtering operation can be performed by using IMFilter. Okay, so IMFilter requires two arguments, two input arguments. Original RGB means the image over which the filtering is to be performed, and the filter mask. H is the filter mask here, and then the display the image. Okay, so only 3 commands are required to perform the filtering operation by using Matlab. By using Matlab, I am saying. Okay. Now, second major area of this fractional order is the age detection. Okay. So, what is age detection? The primary goal of the age detection is to detect changes. Okay. So, how edges or sharp edges are defined? Whenever there is a sudden or large change in a pixel value, then such pixel values are regarded as edges. Okay, regarded as an edges, and during that particular edges you will find large gradients. Okay, so what for this reason we use a gradient operator. Okay, so there are 2 very commonly used operators. One is a Prewitt operator and second is the Sobel operator. As we have 2 directions like number of rows and number of columns, so these 2 operators are divided into vertical operator as well as the horizontal operator. Okay, and how we get, okay, before explaining that, I'll briefly explain how we get the age map. So to obtain the age map, what we have, input is an image, then we apply a gradient operator, okay, by using this equation, and then by performing a simple thresholding, whether the gradient is greater than threshold or less than threshold, will perform that particular operation to generate age map. So the age map is generated. But what are the different gradient operators? So Prewitt and Sobel, these are the two gradient operators, and it's a two-dimensional signal, so we can apply in two directions, vertical and horizontal. If we carefully see all these four masks, okay, this can be also called as mask, this vertical as well as horizontal in both the cases, then the total coefficient addition is 0. Okay, for example, see horizontal Prewitt operator. Okay, so the first row is -1, -1, -1, so -3. Second row is 0, and third row is +1, +1, +1, so +3. -3 plus 3 is 0. You'll find this in all the rest of the horizontal operators as well as vertical operators. So you can perform this edge detection by using simple 2 or 3 commands. Okay, so by using edge command, so there is inbuilt edge function to perform the edge detection. Okay, I'll not go in detail now. Okay, so we'll start with what are the different fractional calculus applications in image processing. Why I explained that all the operations filtering and edge detection, because I am focusing on image enhancement of applications and edge detection applications of fractional calculus. Okay, that's the reason I explained the basics. So there are several areas where we can where the fractional calculus is currently being used. Okay, first, image enhancement, denoising. So enhancement is, I'll explain it a bit later. Denoising, edge detection, then segmentation. Even they are used in fusion also. Okay. Then encryption, compression, restoration, registration. I mean, there is no any area where you'll not find the fractional calculus, use of fractional calculus. Okay. So almost every area, right from enhancement, okay, to restoration, you'll find use of fractional calculus in image processing. Okay, so how this fractional calculus is typically being used in image processing flow, or what is the typical flow? First, we create an integer order method. So by using an effective operator or a model or equation, okay, ordinary differentiation or integration is selected. Okay, so once we have the integer order method, then what we'll do, we'll apply a fractional order method. Okay, so there are several fractional order methods like GL method or RL method or Kaput definition. Okay, so these ordinary differentiation or integrations that are generalized in the first step are converted into the fractional order by using these different definitions, RL, GL or Kaput. Okay, and then what we'll do, we'll perform the numerical approximation, okay, to the fractional order operator or model that is generated during the second step, which will be calculated by discretization methods. Okay, so this is the fractional order image processing flow. Now we'll explain all the it's not possible to explain all papers, but most of the major papers, okay, or major research in image enhancement using fractional calculus. So I'll be, as I told you, I'll be explaining two areas, image enhancement and edge detection using fractional calculus. Okay, so before understanding this image enhancement, fractional calculus in image enhancement, we'll first understand what is image enhancement. Okay, and then, because this is important to understand the importance of fractional calculus in image enhancement. So basically, we perform image enhancement to improve the quality or pictorial quality of image and to enhance information content of original data from a specific analysis. So when I want to improve or when I want to enhance certain region of given image, I'll perform the image enhancement. Okay. What are the applications? You'll find image enhancement applications in highlighting the characteristics of target in the image and extracting the target features from the digital image. Suppose I want to highlight certain portion of given image, entire image. Okay, then you can do it by using image enhancement operation. How will you do that? We'll perform image enhancement over that particular region only, and no enhancement for the rest of the region. Okay, this is how you can highlight the image. There are two methods for image enhancement. One is the frequency domain method and spatial domain method. So in spatial domain method means you are directly working, or you are directly manipulating the pixel values of given image. Whereas in frequency domain method, we perform, or we enhancement is done by applying a transform method like DW, discrete wavelet transform, or Fourier transform, and then we manipulate these frequency coefficients, and then we apply inverse transform, and then we get the pixel values. This is, I mean, these are the two very popular methods in image enhancement. Remember this concept that low pass filter is used to remove noise and high pass filter is used for enhancing the high frequency edge signal. Okay, so whenever you want sharpening of the image, remember smoothing and sharpening is part of image enhancement. Okay, so whenever you want to perform smoothing, you have to use low pass filter, and when you want to perform sharpening, you have to use high pass filter. Okay. Now, one of the very important concept is that the integer order differential operators, okay, like what are the different integer operators, Sobel or Prevet or LOG, Laplacian of Gaussian operator, all these operators performs better for high frequency features of an image. Means whenever there is a high frequency region, or whenever you want to extract high frequency features, then these integer order differential operators like Sobel or Prevet will work perfectly fine. But the limitation of these, or the drawback of these operators, are their performance deteriorates significantly when applied to smooth regions. So that means these operators will not perform better in case of low frequency features. Okay, first reason why, this is the very first reason why we are using fractional calculus in image processing. Okay, now what happens when we use a fractional order differential operator, then that particular differential operator will preserve high frequency contour features. That means high frequency features will be preserved. Not only these high frequency features will be preserved, but low frequency texture details will also be improved in smooth area. Okay, so there is a twofold advantage of using fractional order differential operator. First, it will preserve high frequency features. Second, it will improve the low frequency texture features. Okay, now remember, whenever the fractional differential mask is can be used in different applications, it can be used in different sizes, like I told you, 3 by 3, 5 by 5, or 7 by 7, or sometimes even 11 by 11. Okay, and one can have 8 different directions for that particular mask. Okay, so these masks can be of single direction, multi-direction, or non-regular direction. So you'll find the mask in some research papers, you'll find in only one direction. In some research papers, you'll find in multi-direction, and some very rarely you'll find non-regular region. So I have a negative x coordinate, means left hand side. I have negative y coordinates, means downwards. I have positive x coordinates, means right hand side of the axis. Positive y coordinates means up from the origin. Okay, left downward diagonal, right and left downward diagonal. Okay, upward and downward. So what you can see here in the figure, right from 0, 45, 90 up to 315. So there are total 8 directions. So most of the papers you will find this 8 fractional differential mask. Okay, applied over these directions. So the first 3 by 3 fractional mask operator, which is developed for medical image enhancement. Okay, so you can see here the CT image, original image, as well as the image that is enhanced by histogram and image that is enhanced by different fractional differential mask operators. Okay, so you can see here in the as I told you that we need two directional mask. One is in x direction and one is in y direction. Okay, so you'll find that this is a unidirectional mask. Only one direction mask is there. So first coefficient is alpha square minus alpha divided by 2. The center coefficient is minus alpha and third coefficient is 1. What is alpha here? Alpha is the fractional order that is used in the x-axis. Similarly, mask of y-axis is in the vertical direction, whereas mask of x-axis in horizontal direction. Okay, so what we have to do is, the way we apply the Sobel mask or Prewitt mask in vertical and horizontal, I'll show you once again for better understanding. Yeah, these are the vertical and horizontal mask. In the same manner, okay, the way we use the Prewitt operator and Sobel operator in the conventional image processing, we apply the mask processing, or we perform mask processing by using these two masks. So you can see here, by using this 3 by 3 fractional differential mask, this around 0.8 of the order 0.8, we get better enhancement as compared to the histogram. Okay, so histogram is the conventional. So what usually we have to do, we have to compare with the conventional image enhancement algorithms with your fractional differential mask operator algorithms. Okay, so enhancement is better. Okay, these researchers proved that the enhancement that is obtained by using the shown fractional differential mask with 0.8 order is better as compared to the original histogram enhancement operation that is used in the conventional image processing. Okay, this is another example of 5 by 5 fractional differential mask operator. So what the authors did here in this case is, instead of using a 3 by 3 mask and in earlier case and in only one direction, they developed a 5 by 5 mask. Okay, and the mask is shown in this slide. You can see here with different values of coefficient, mask coefficient. The center coefficient value is 1 by 8. Okay. 8. 1 into 8, that is 8. And the enhancement, that this remember, this mask 5 by 5 fractional differential mask is for medical image enhancement. So as earlier I told you that most of the applications, okay, in enhancement you'll find in medical image processing. So the authors compared these 5 by 5 fractional mask with the normal histogram equalization or histogram enhancement process. Okay, and then what they found, that original image, they this algorithm performance is compared by using 3 performance evaluation parameters. First one is the mean value, second one is the clarity, and third is the entropy. Okay, so you can see here mean value should be low. Okay, clarity should be higher and higher, and entropy should be higher and higher for better enhanced image. So you can see here original image, these 3 values are shown. Hopefully I hope these figures or the numbers can be seen on everyone's screen.
Yes, sir. It is visible.
Okay. So original image is having mean value of around 165, clarity of 16.65, and entropy of 6.84. What the authors did, the alpha, that is order, fractional order, they have taken a fractional order from 0.2 to 0.8. Okay, and they obtain 3 values. Okay, 3 different these performance measure. Then what they found, that around alpha equal to 0.8, the mean value is reduced, clarity is very good, that is around 26.10 compared to the original 16.65, and entropy is also enhanced from 6.84 to 7.40. Okay, but remember the contrast in this case. Okay, so I mean, it's very interesting to see. I mean, not all the parameters will be better for all the values of alpha. Okay, for example, consider alpha equal to, that is fractional order equal to 0.6. Then in that case, clarity is 25.79. Okay, definitely it is better than the original image, but entropy they found is the highest, 7.52. Okay, 7.52 when alpha equal to 0.6. At the same time, when the authors did experiments at alpha equal to 0.8, then what they found, clarity is enhanced compared to 0.8, 0.6, but the entropy is reduced. Okay, so from 7.52 to 7.40. What I mean to say here in this case, that remember, whenever you are increasing your fractional order and generating your or creating your 5 by 5 mask, then at that time it is not the case that all the evaluation of performance parameters will be increased. Okay, this is what I want to convey from this slide. Then the third application, okay, I'll just magnify. The third application here is V means fractional order. Okay, some authors will use alpha, some authors will use V. Okay, so it is a 3 by 3 mask, that is again, and this mask is used for image denoising and enhancement. Okay, medical image enhancement. Okay, this is, you can see here is a MRI image. Okay, so these are the two masks. Okay, I'll show it once again. Okay, so mask left hand side, that is FIA1, here it is shown, and the right hand side mask is FIA2. Now in this case, you can see here, compared to the FIA1 mask, this left hand side mask, then the mask that is a adaptive mask that performs better. The second mask performs the better, and the author shown that the performance that is obtained by using adaptive fractional differential mask, okay, for different values of this, that is obtained by using different values of alpha or V in this case, is better compared to the conventional application. This is very interesting application, that is enhancement. Okay, so this is a fractional derivative filter that the authors developed for contrast enhancement. Now so this is again, the authors developed a fractional mask of 5 by 5 size. Okay, and what is the order they put? The order they selected, alpha equal to 0.358. Okay, so by using this 0.358 alpha, they created a 5 by 5 mask, and then if you see original image and the filtered image. Okay, so the filtered image, or in this case which is shown as proposed filter, okay, so filter image is much better or enhanced as compared to the original image. Okay, so this is understanding from the visual understanding of the person or visual perception. Okay, but we have to prove also, okay, by using standard image processing operations. So right hand side of the figure which is shown, okay, so two histograms are shown. For the figure B, which shows the original image histogram, and figure D shows the histogram of enhanced image, which is enhanced by using a fractional order mask. You can see here it is a kind of a best a histogram that can be observed by using this or after applying the filtering operation. Okay, so in this case what you will see, most of the pixels, okay, in the original image histogram, most of the pixels are towards the black side, okay, left hand side of the figure. Means rarely you will find pixel values near to the positive side, that is higher value, means brighter side, okay. So ideally what we need, as I told you earlier, to understand the histogram, okay, that ideally we want all the pixel values with equal numbers, okay. This is what is expected. So we cannot say it is ideal output, but it is going to close to the ideal one. And last application that I'll explain in the image enhancement is the Landsat image enhancement. That is satellite image, how the satellite images are enhanced by using this fractional order mask. Okay. So what they did, the authors did, now in this case, so the main difference between this research, okay, current research that I'm showing as compared to the earlier one was that all the earlier research uses only one mask, either 3 by 3, 5 by 5, 7 by 7, 9 by 9, or whatever the value. But first time, the authors used three different types of masks, 3 by 3, 5 by 5, and 7 by 7. Okay? And they fused together the the enhanced image after applying 3 by 3, 5 by 5, and 7 by 7. They combine together or fuse together, okay, to obtain the final image. And surprisingly, the results that were obtained by using such kind of arrangement was better compared to the individual filter mask. Okay, so this is very interesting application. You can see the paper also I written, comparative analysis of Landsat image enhancement using fractional and integral differential operators. Okay, last year paper. So in 8 direction they used this mask, and this is 3 by 3 mask. Okay, yeah, okay. So 3 by 3 mask, 5 by 5 mask, and then 7 by 7 mask. So what you have to do is, you have to, V means alpha, okay, fractional order, that you have to put the fractional order value in this that particular values. For example, minus V is there, so it is suppose 0.4, so 0.4, 0.4, 0.4, okay. This will create your mask, and then you have to perform the filtering operation, okay. And then what the additional thing that the authors did in this case is the combining all three filter mask responses. Okay. So till now we have discussed all the image enhancement applications. Now the second application or second area is the edge detection. So what is edge detection? Edge detection is identifying the change in the or sudden change in the gray level values. Okay. So how we identify or recognize edges as under the classification of high frequency signal. Okay. So whenever there is a sudden change, we call as a edge, or sudden gray level value change we call as an edge. And this edge detection is very important, okay, to extract the seen objects. Okay, suppose you want to, suppose there is an image, okay, and that particular image there are several objects, okay. Then to segment that particular object into an individual object, we need to separate out the each and every component. Okay, so how to identify this? First you have to perform the edge detection, so you can border out all these individual elements or individual objects, and that's the reason why edge detection is the first step in the segmentation. Okay, now there are several integer order differential operators for use for edge detection, like Roberts or Prewitt or Sobel or that already discussed in the previous image enhancement application. Okay. But what happens, the conventional operators, okay, or the first order derivative operators, LOG, Laplacian or Gaussian, will cause a thicker edges. Okay, so whenever after applying this filter, it will result in a thicker edges, okay, which will remove some image details. Okay, whereas if you go further from first order filter to the second order filter, or second order derivative filter, then what happens, they have very strong response to fine details, okay, but they are very sensitive to noise. Okay, so noise sensitivity will affect on the performance of second order derivative filter, whereas first order derivative filter will have the loss in the image detail. Okay, and that's the reason why, to solve these two difficulties, because of the first order derivative operator and the second order derivative operator, we use fractional order derivative. And what are the advantage of fractional order derivative? These fractional order derivative operators, which are used in edge detection, preserves low frequency contour features in smooth area. Okay, they will not make thicker edges. Second, it will maintain high frequency marginal features and enhance medium frequency texture details. Okay, and they are not very important. Very important is they are not sensitive to noise. Okay, now the first this was in ICVIP paper 2018. So image edge detection application that is developed by using fractional order differential calculus. So you can see here total of 9 directions. Okay, so negative direction, then normal direction, then y-axis and x-axis, negative, normal, and the diagonal. So what we have, total of 9 directions. So you can see here, okay, x-axis negative direction. I'll explain with x-axis negative direction. So the first coefficient is 1, second coefficient is minus v, and third coefficient is v square minus v by 2. Okay, if you remember that typically the mask will remain same. Okay, so typically the mask will remain same in most of the applications. Okay, how we are applying, in which directions you are applying, okay, in different areas, it will vary. Similarly, one can have x-axis normal direction, okay, starting from 1, topmost coefficient minus v and v square minus v by 2, where in this case v is order. Okay, so if you apply these 9 direction fractional order differential mask, and then if you combine all 9 masks, okay, then you can have this, you can generate image edge detection using this kind of mask. So this is one alternative. So one total 8 masks you have to operate, you have to apply and then combine the response. Or second operation or second option is combine the mask initially. Okay, instead of combining the responses, okay, what you are doing, combine the mask in the initial phase and then apply. Okay, apply the mask. So the final, you can see here the final mask template. So remember, this choice of using the technique is of yours. You generate 8 different masks, you produce 8 different responses, and then you combine first. Second, instead of generating 8 different masks, you construct final mask, generate a response, no need to combine. Okay, so it is user's choice or designer's choice. So you can combine this mask and you can have this final mask template in this form. Okay, this is what the authors obtain for different values of orders, alpha for order equal to 0.3, 0.6 and 0.7 and 0.8. So you can see here at the fractional order 0.8, the response that is obtained, okay, because we are interested in detecting the edges, okay, compared to this is very, better as compared to the original one. This is another application of what the authors did, okay. So they developed different masks, total 4 masks authors developed: mask 1, okay, then mask 2, mask 3, and mask 4, okay, at different values of alpha. So, and then they compared the responses for Alzheimer disease detection on MRI images, okay. So this is just an experimental study. So authors did that different mask study, and they found that 3 by 3 mask performs better compared to all other masks. Okay, no need to go for complex mask like 7 by 7 or 9 by 9 or 11 by 11. This is another very interesting application, that is a cold rock fracture image detection. What I'll explain this about first, that you have to identify fractures that are present in the cold rock by using this fractional order differential operators, and the purpose is better served by using 3 by 3 mask as well as 4 by 4 mask, 5 by 5, 6 by 6. All the different fractional order surveil operators are shown here, and you can see here, as I already explained, 3 by 3 mask will serve the purpose. No need to perform the complex operations, because we are interested only in identifying the edges. Okay, this is second last application, interesting application I'll explain, and then we'll see the one implementation in Matlab. Okay, so this is the last year's paper where the authors detected faces using fractional order PCA and SVM. So what the authors did, they developed 3 by 3 fractional differential operator, as it is shown right hand side, okay, alpha divided by 8 alpha minus alpha and all these values, okay, 3 by 3 mask, okay, and they select this alpha value order equal to 0.5, okay, fine, and by this fractional order they perform the phase age detection, okay, first, and they calculated the features, PCA features, okay, and then by using SVM classifier they classified the faces. I'll show you this. These are the first row shows the original face images. Second row shows edges that are obtained by using Sobel operator. Okay, that is the conventional image processing operator. And third row shows the fractional differential operator. Edges that are obtained by using a fractional differential operator. So you can see the edges are very clean and informative. So you can very easily extract important features from the fractional differential edges as compared to the conventional Sobel operator. So what they did, they calculated the accuracy in the end, and they found that, phase detection accuracy, they found that the phase detection accuracy that is obtained by using fractional differential mask features are much better than the Sobel operator feature, okay, mask features. And this is what the observation in last year's paper, where they detected face images. And the last application for age detection is used in again in the different areas of image processing. Like that's the reason why I shown here. The authors proved that they can used in linear images, non-linear images, medical images. The same mask. What is interesting here is the same mask can perform in different areas of applications. Okay, so yeah, this is the mask that proposed in the paper that is shown. That paper was appeared in 2016. So it is 5 by 5 mask, which is applied for x direction, and 5 by 5 mask in the y direction. Okay, and these are the sample images from the database they use. And what the authors found that, I mean, you see here the first row as first row, canny. Canny means it is a conventional image processing operation. Okay, age detection operation. And the authors proved that at different, and the authors calculated MSE, PSNR, okay, for different values of alpha fractional order. And this calculation of fractional order is ranging from 0.1 to 0.9. Then for lower orders at around 0.2 or 0.1, medical image enhancement performs better. You can see here for alpha equal to 0.1, image enhancement in medical area is better. Okay, remember MSE lower is the better. I'll explain a bit later. MSE and PSNR. Okay, whereas for the linear images, alpha equal to or the order 0.5 works better, and for non-linear images or natural images, alpha equal to 0.2 works better. Okay, that means you cannot have a same mask for for different images. Okay, so this is very interesting outcome of this experiment, that there are three types of image processing images: linear images, non-linear images, and medical images. And enhancement is obtained at different alpha values. Okay, so that means if you want to perform medical image enhancement, you cannot use alpha equal to 0.5. You have to go for alpha equal to 0.1. This is the observation. Okay, for 3 by 3 mask. Whereas if you use 7 by 7 mask or higher and higher mask, no need to go for the different values of alpha. That means if you see the table, second table, 7 by 7 mask at fractional order equal to 0.1, then most of the areas of images, linear, whether it is a linear image, non-linear image, or medical image, you'll find that both are all are enhanced at lower fractional orders. Okay, no need to go for other fractional order mask. Okay, so before implementing one example, we'll see a few performance metrics. That is, first matrix is MSE. Okay, so I'll just show you here. You'll find that most of times you'll find MSE and PSNR. Okay, so when you want to perform a comparison between your algorithm and the conventional image processing algorithm, you'll need a performance matrix. Okay, so most of the time you'll find MSE, that is mean square error, and PSNR, that is peak signal to noise ratio. So what is MSE? MSE is the mean squared error. Okay, and it is nothing but average squared difference between the estimated values and the actual value. Now, what is the estimated value and actual value? When we use MSE, suppose you have an original image. Okay, you have an original image or actual image, and then if you have performed enhancement by using fractional order calculus, then you will have enhanced image. So what you have original image and enhanced image. Okay, so the difference between enhanced image and the actual image is nothing but the MSE. Okay, so this MSE is a measure of the quality of an estimator, Remember, it is always non-negative. Okay, it is always non-negative, and lower the value, okay, better is the quality. Okay, so values closer to 0 are better, means lower and lower values of MSE is nothing but the image is better and better. Okay, and how to compute this MSE? MSE can be computed by using this equation 1 by Mn summations, two summations, because rows and numbers, n equal to 0 to n minus 1. One is for rows and one is for second one is the columns. Iij minus I prime Iij square, difference square. Okay, where what is Iij is the original image, and what is I prime Ij is the degraded or enhanced image. Okay, remember why I used degraded and in bracket enhanced, because even sometimes you need to calculate MSE for degraded as well as MSE for enhanced images. Okay, and what is M and N? M and N are the M equal to number of rows and N equal to number of columns. Second very important performance metric is the PSNR, that is peak signal to noise ratio. That is a ratio between the maximum possible power of a signal to the power of corrupting noise that affects the fidelity of representation. Okay, so it is the signal, basically it is a signal to noise ratio, and we are calculating peak of that particular ratio. Okay, now what happens in real life scenarios, each image is having very wide dynamic range. Okay, and because of very high dynamic range, the peak signal to noise ratio or PSNR is usually obtained in terms of log scale. Okay, logarithmic decibel scale. So you'll find PSNR in dB. Okay, why? Because of the large dynamic range of the image. Remember, higher the PSNR, better the quality of reconstructed or compressed image. Okay, it is opposite to the MSE. MSE lower is the better. Here higher is the better. And how to calculate PSNR? PSNR is 10 times log to the base 10 max I square divided by MSE. Okay, once we have calculated MSE by using equation, earlier equation, and if we know the maximum possible pixel value of the image, that is max I, then take the square divided by MSE and take the log and multiply it by 10. You will get the PSNR value. Okay. Another way you can also calculate by using PSNR by using the second equation, 20 log to the base 10 2 raised to b minus 1 divided by square root of MSE, where b is the bits per sample, but the first equation is very common. And third is the entropy. Okay, so entropy is a statistical measure of randomness that is used to characterize the texture of an image. And how entropy is calculated? By using this equation H equal to minus summation of G equal to 0 to 255. Why we have taken 255? Considering the image is 8-bit, ranging from 2 raised to 8 equal to 256. So G will be ranging from 0 to 255. Okay, PG log to the log of PG, where PG is the normalized histogram counts written from the IM histogram. This is with related to the Matlab. Okay, okay, fine, that's fine. Now we'll implement the astronomical image enhancement. This is done by one of our students, that is astronomical image enhancement. The goal is to enhance the astronomical image using fractional order derivative. And what are the different performance parameters that were evaluated was entropy, PSNR, and the mean values. Okay, what were done also, were tested what is the effect of alpha greater than 1. Okay, so most of the researchers, they have tested alpha equal to 0 to 1 only, between 0 to 1. And what we did, we created 5 by 5 fractional mask in 8 direction. Okay, so the first step what we followed is read the astronomy image. Okay, so what is the input image is there? as astronomical images are color images, so the first step after reading is to convert into grayscale. Okay, so I'll show it to you. This Matlab screen is visible, sir.
Yes, sir. Yes, sir.
Okay.
It is visible.
Okay, so what I'll do, these are the images. Once I'll show the images. Yeah. So these are the astronomical images. You can see a lot of noise that is contained because they are collected from long distance. These, I mean, signals that are coming from long distance. Okay, fine. So these are the examples or samples of astronomical image. So what we'll do, I'll read this sample images. Okay. I'll go step by step. I'll show it to you. That's better to understand. I'll clear it. Okay. So, hi. Now what I have in the workspace is the astronomical image. I want to see this image. I'll show it. Okay. So this is astronomical image that I want to enhance. Right. Now, what is the first step? The image is in the RGB. So what I'll do? I'll convert into the grayscale first. Okay. Okay. To convert. Okay. One. Okay. To convert grayscale, what is the function in MATLAB? RGB to gray. Okay. Suppose I want to show this. I want to see this grayscale image. BW. So you can see the grayscale image. Next step is to convert this into double format. This is for just for MATLAB purpose. Okay. Now this is very important step. This is a GL mask that is with the, as I told you earlier, that we are tested. No one has tested what is the effect of alpha greater than 1. Okay. So what we thought of testing the algorithm between the order higher greater than 1, that is 1 to 2. So this function, okay, h1 equal to GL mask will create the mask, GL mask, with the order 1.1, and we need step size also, correct, with step size 0.3, and what is 5 is the size of the mask, 5 by 5. Okay, so let us say I want to create a mask. Okay, so it is better to write here first to understand. Order, okay, order, step size, and what I can say, size of, okay, size, okay, size of the filter. Okay, this is what the function does. Okay, so here order equal to 1.1, step size is 0.5, and the mask size is 5. Okay, I'll show this. So this is your mask, final mask that is generated. So h1 equal to 0.2068. Okay, so this is 5 by 5 mask for order and step size. And what is the, how it is generated? I'll show it to you. This is a function. Okay, so alpha, that is order, step size h, and the size n. So what we did, again coming back to the presentation, we compute the binomial coefficient. Okay, where it is? Okay, we compute the binomial coefficient first, and only first 3 coefficients. Okay, 1, 2, and 3. where it is. Only first three coefficients, 1 alpha and alpha into alpha minus 1, 2 raised to h alpha. These three coefficients are selected once we have binomial coefficients that are obtained from the GL definition, and the mass that you have seen here, h1, okay, 0.20680, 0.20680, 0.2068, okay, is nothing but the mass, that is, by substituting alpha equal to that particular value, we will get this mass. Okay. So what we did, we generate a 5 by 5 mass, and then we perform the filtering operation. Okay. So two mass are generated just for comparison purpose, H1 and H2 for so H2, you can see here H1 and H2, two mass are generated. H1 is for 1.1 and H2 is for 1.2 order. Now next step is filtering operation. I told you initially, okay, filtering operation. So for filtering is very easy in Matlab. So just to write a single command, IM filter. So what you have to filter? There are two input arguments, BW. What is BW here? BW is your input image, okay, that you want to enhance. And H1. H1 is the mask that you have created, fractional order mask. So I have created two masks, so I'll create two images, F1 and F2. Okay, if you want to see this, F1. Okay. So this is okay. So this is your enhanced image, removing the noise. Now, how we can compare whether it is enhanced or not? I'll first show this images. Okay. So we have original RGB image, then we have original grayscale image, and then you can see here enhanced image with alpha equal to alpha equal to 1 and alpha equal to 1.2. Okay. So alpha equal to 1.2 is much better than alpha equal to 1. Okay. But how we have to prove this? We have to prove by calculating. This is visual inspection only. Okay. So by calculating the different values. Okay. So directly, without wasting time, I'll show it the final values. Okay. So you can see here the original image entropy was 7.03. Okay. Now the image entropy after applying first mask, okay, first mask H1, we obtained as 6.9. That means this image is inferior compared to the original image. But when we apply second mask, that is alpha equal to 1.2, okay, what we obtain with the image with very high entropy compared to the original image. Original image entropy was 7.0372, and now the entropy of enhanced image by using this fractional order mask is 7.42, which is greater than the original image. Okay. So PSNR also, I'll show you PSNR 1 and PSNR. Okay. So remember, even though the entropy of the first case, okay, was lower, but the PSNR is higher. That's why initially in the initial session timing of the session, I told you not necessarily all the time all the parameters should be towards the ideal range. Okay. So in the same way, you can apply this with the medical image enhancement. Okay. Okay. Sir, whether time is over or we have 5-10 minutes?
Sir, you can take 5 minutes more. No problem, sir.
Okay, just I want to show speech processing in short.
Okay, no issues.
Just within 5 minutes, I'll finish this.
Okay, sir.
So this, I mean, most of the focus was on image processing, but there are very interesting applications in speech processing also. Remember, okay? So the basic idea that is used in speech processing and medical signal processing. I'm not talking about medical image processing, but medical signal processing is the LPC, that is a linear predictive coding. So, how the research in speech processing started, I'll give one example. That was the first paper in 2006 that the linear predictive coding analysis, which is performed and it is very popular in mobile and all other analysis purpose, the speech or voice analysis purpose, that LPC coding, linear predictive coding analysis, was performed first time by using a fractional technique or fractional order calculus. There it started. Then it was a gap of around 4 or 5 years. Okay, there was no any paper. Then suddenly in 2013, based on the same concept of linear predictive coding analysis, there were several papers, several in the sense 5 to 6 papers that appeared on the medical signal processing as well as the different areas of speech processing. So just I'll show the area where you can use. Remember, these speech enhancement you will not find. So you can see this as opportunity where you can use this fractional order speech processing for different areas in speech. Compared to medical, I mean speech processing area by using a fractional calculus theory is very less explored. There are a lot of areas, open areas where you can use the fractional order calculus in speech processing. So hardly there are 4 to 5 applications you'll find in modeling of voiced and unvoiced speech. Then in medical signal processing, as I told you, that in EEG signal as well as in PVC signal, then EMG signal and EEG signal classification. Okay, so this medical signal processing is again all the research EEG, ECG, EMG, and EEG again is based on a concept of LPC only. Okay, so every paper was based on the concept of the first paper of LPC. Okay, so I think I have that mention of that particular paper. Okay, fine. So thank you all. Thank you, sir.
Welcome, sir. Thank you, sir, for your wonderful talk, and special thanks for speech processing. Okay, there are few questions from participants, sir.
Okay, sir. Okay, please.
Okay, now with your kind permission, I would like to ask some of them, sir.
Yeah, sure, sir. Please.
Okay, the first question from my colleague, Dr. Pranal. How can we implement a 5x5 fractional mask in Matlab? Do we need to generate Matlab code, or we can use an inbuilt command?
Okay, sir. So based on fractional order, the mask will change. That's fine. Okay, first thing. Second, I have shown here the same mask, 5x5 mask. Okay, sir. Once again, I'll show it to you. I think H1 was the mask. Okay, this is the mask. Okay, so you can use inbuilt MATLAB function. What you have to do is you have to take care of alpha, H, and N. Okay. And what was another part of that particular question?
Do we generate MATLAB code? It's enough, sir.
Okay, okay, fine.
I think he got his answer.
Okay, fine.
Okay. Also, second question from Dr. Krunal. How can we find entropy and clarity?
Okay, entropy, I have shown the. This is the equation for entropy. Okay, so H equal to minus 0.25. I think. I hope you can see this, sir.
Yes, sir. Yes,
H
sir.
equal to this equation, or
Yes,
even
sir.
if you want to perform in Matlab, I'll just show you. Okay, entropy of the image. Image is in this case is let us say BW. Yeah. Okay. So entropy. There is a command inbuilt function. Okay, entropy. No need to worry about the equations and all. You thanks to Matlab. BW.
Okay.
Okay. So this is the entropy. 1.17. You can very easily calculate the entropy. This is okay by using the inbuilt command entropy.
Okay, sir.
And for clarity, I'll send. I mean, I don't have that right now. That equation and all.
Okay, no problem, sir. Third question from my colleague Dr. Mira Chudasama. Any suggestion for the books which include layman understanding of these terminology like mass, filters, entropy, its MATLAB code?
Basic image processing by Gonzalez. I'll just I'll type in this chat box once. Digital image processing. Yeah, I think hope you can see this.
Yes, sir. Yes, sir. Yes, sir. We get it. Okay.
So this book also contains this supplementary book of this main book also contains MATLAB codes. So it is very easy to understand the image processing concepts.
Sure, sir. Okay. Okay. Thank you for answering this question, sir. It is very informative session, sir. You have discussed about introduction to image processing using MATLAB, fractional calculus in image processing, astronomical and medical image enhancement using fractional order derivative, image age detection using the fractional mask, speech processing, and all topics are very interesting and useful concepts in special functions and fractional calculus. Sir, please stop your sharing, sir, so we can view something for you.
Okay.
Thank you, sir, for accepting our invitation and sharing your deep knowledge from your busy schedule. I hope our participants have enhanced their knowledge from this session. I will be a great pleasure for us to listen you again at our university in future events in offline mode. With your permission, I want to present e-memento for you, sir. This is token of love from our department and Charusat family. Please accept it in virtual mode.
Thank you, sir.
Thank you, sir, once again. Thank you very much, sir.
Okay. Can I leave now, sir?
Okay, sir. Sure, sir. Okay. I request to all participants kindly fill the feedback form which was shared in chat box. Dear participants, next session will start at 2:30 p.m. in afternoon. Dr. Devendra Kumar will take this afternoon session. Okay, good day. Take care.